Hello students, welcome back to this part. In this part we will discuss cause of electromagnetic induction. The change in magnetic flux causes electromagnetic EMF and the concept of Motional EMF. So let's start. Let's start with the topic Faraday's laws of induction. In the Faraday's laws of induction we will discuss about how magnetic flux changes with respect to time t and how it gives induced EMF across the coil connected with it. After that, when we have induced EMF, definitely we would consider induced current across the coil. So, first of all, we would like to understand the term given over here. E stands for electromagnetic EMF, electromagnetic force, that is EMF. It is just a voltage source, we can say, and is the number of turns of the coil. Phi is the magnetic flux and T is the time with respect to which flux is getting changed. Now, we will understand the EMF induced across the secondary coil. So, in the case 1, when we are bringing magnet towards the coil and the magnetic field strength is getting changed with respect to time t across that area. So, what? Magnetic flux will change, because already we discussed that magnetic flux is a function of B into A cos of angle between them. So, we can express area. Area is just equal to the length multiplied by the breadth. So, length is what? When velocity is just velocity, when magnet is moving with velocity v towards the coil. So, we can understand B into A cos of theta, and now some current is induced across the secondary coil that is read by this resistance R, and through which we are connecting a voltmeter to read the value of voltage. Now, similarly, same phenomena. If we replace that magnet with current carrying coil, so means if I am considering there is a voltage source through which DC current I is produced, we are considering this as primary coil. Now, current is flowing across the primary coil. We know that whenever current is flowing across the circular coil, magnetic lines of force will also pass through the secondary coil. So, we can denote it like this way. Means due to current I1, there is a magnetic lines of force or magnetic strength B1 also passing through the area of the secondary coil having area E2. And we are interested to know the value of induced EMF across the secondary coil. That induced EMF is due to the change in the magnetic flux, and that magnetic flux is a function of magnetic field strength, maybe due to artificial, maybe due to natural magnetism. This time we are considering artificial magnetism due to current carrying coil. Now, when this magnetic field B1 is passing through the area of the secondary coil, so we are getting flux produced is equal to B1 is the magnetic field due to the current flowing in the primary coil, area of E2. And now we are interested to know the induced EMF. That induced EMF is equal to the change in flux with respect to time t. This is giving us V1 E2 divided by delta t, and the change in the magnetic flux also. So we can get this is the induced EMF in the secondary coil. And if we are having resistance R across this, definitely some current I is equal to induced current by R. So means induced current I is equal to the induced EMF by resistance R connected across this, and already this is equal to delta phi upon delta t, the modulus of this value divided by the resistor. This is all about induced EMF and induced current across the coil connected to it. Now, we will discuss about cause of magnetic flux changes. So, cause of magnetic flux means already we know that E is equal to delta phi upon delta t. This magnetic flux can be changed if V is changing, or area is changing, means varying we can say, or either it can be due to orientation. Orientation means coil is rotating into that uniform magnetic field. So the case 1 we will discuss about when magnetic field is changing or area is changing. The first part we will discuss about area is changing. So initially you can consider there is a coil having area A1 due to some external effort, if you change the area, it can be A2. So we get change in area is equal to A2 minus A1, that is change. Now we want to find out EMF. EMF is equal to change in flux with respect to time t, and that is equal to B is uniform, so delta A by delta t, and that is equal to this. But we must understand the theta between them. Why? Okay, it is equal to 0 degree because the direction of magnetic field is into the plane of paper, that is along k means z axis, into the z axis, and area vector is also into the direction, so A is also into the same direction. When we want to find out the cross dot product of these two, we are getting this is equal to B into delta A by delta T, and that is equal to the EMF induced across the ends of the coil. Second part, if this is about magnetic flux change, if the angle between the loop and the field is changing, means we are talking about orientation. Orientation means either coil is rotating with the direction of magnetic field, or magnetic field is changing with respect to the area vector of the coil. So we can say that phi is equal to BA cos of theta. So means we want to find out induced EMF, that is equal to change in flux delta phi by delta T is equal to BA, because these are uniform. So now it is related to dy dt of cos of theta, and this is equal to B into A sine of theta, like this. And we will consider a negative value, but we want to find out induced EMF, then we have to consider the magnitude of this value. So E is equal to n, if there are n number of turns, BA sine of theta. But you know that theta is the angular displacement that can be represented as a function of angular velocity. So it can be sine of omega into time t. So this is the induced EMF across the coil when coil is rotating in the uniform magnetic field. So we will discuss about the third part related to this, that induced EMF due to change in the angle theta. So already we knew that phi is equal to B into A into cos of theta. So three cases we consider. If we consider theta as 90 degree between the magnetic field and area, so flux will be 0. Of course, cos 90 is equal to 0. Similarly, as 45 degree, flux would be greater than 0. And at theta equal to 0 degree, when the angle between the magnetic field and area vector is same, we can consider flux is just the maximum. So phi is equal to BA cos of theta, that is equal to BA cos of 0 degree, and finally it is equal to maximum value BA, that is equal to phi. So means induced EMF due to change in theta. Now we will differentiate this value cos of theta, we'll get sin theta, and we know that if we are talking about induced EMF, so induced EMF would be a function of sine of theta. We know that sine theta will be maximum at 90 degree when theta is 90 degree, and when theta is equal to 0 degree, it means induced EMF will be minimum. That's why we will consider the case third. Next case, a current produced by an induced EMF moves in the direction so that the magnetic field it produces tends to restore the changed field. It means we are bringing this magnet towards this coil, and this coil would like to oppose any kind of change due to the magnet taking towards it. So means that magnet would like to restore, means initially the galvanometer shows at 0 deflection. When you are bringing a magnet, what will happen? Deflection in the galvanometer would be maximum when you are approaching magnet towards the coil, but when you are taking it away from the coil, it shows negative frequency in opposite direction. So means it is restoring. Also we can consider, because there was a scientist whose name was Lenz, he stated that this is the best applications for law of conservation of mechanical energy. So means mechanical energy can convert into electric energy, and here we discuss this one, that is E is the induced EMF, and minus and del phi by del t means negative sign is just due to the Lenz law, and it shows opposing behavior. Means induced EMF is produced due to the change in flux. But the tendency of induced EMF would be opposite to the magnetic flux involved with this. So this is about it. Now, applications of Faraday's law. This is very important application. Means it is associated with whenever electric field is changing, it is giving the concept of magnetic field or vice versa. Because in case of electromagnetic waves, we know that whenever a charge is in motion with non-uniform velocity, there are three effects. First is electric field, magnetic field, also it radiates energy. But this time we are not talking about uniform velocity. So if we consider a charge, electric lines of force are getting produced from this charge. It is as it is in a stationary situation. So now a changing magnetic field produces or creates an electric field or vice versa. You can consider means in the Maxwell's third equation, changing magnetic flux will give us the concept of electric field as it is given over here. Like now, come to next point, that EMF induced in the moving conductor. So this is the case of motional EMF. So we can say if magnetic lines of force is out of the plane and we are considering a coil. Now there is a rod A, B. So when this rod is about to move outward or inward, means there should be a relative motion. To move this rod, we can exert external force. It means external power can be delivered. So here we will discuss about how motional EMF is produced or induced. Motional EMF induced or produced due to the motion of the coil into the magnetic field. So we can say that E is equal to del phi upon del T. Phi is the magnetic flux, that is a function of B into area upon delta T. Now we are given magnetic field is uniform, already we considered this value. Then there is a change in the area. So that is delta A upon delta T. Also the angle between area vector and magnetic field is 0 degree this time. So area, now we will consider here area delta A is equal to area final minus area initial. So initially we can say this is actually equal to V into delta T, means this is what? Change in length, that is delta, we can say X, we can consider this part as X, delta X, because it is along X axis, multiply by the length. So this is change in area. So when we will substitute this value in place of delta T, we are getting V into delta X into L upon delta T. So we are getting this EMF is equal to BLV, because velocity or speed is equal to change in length upon time. So this way we are getting motional EMF. So we must understand V is directly proportional to the magnetic field, directly proportional to the L, and also proportional to the speed. Also number of turns, means as we increase the number of turns, definitely EMF across the coil will increase. Now this is the application part, means if electron is moving in the conductor from point A to B, so we can say induced EMF across the end of the conductor can be equal to the potential difference, and that is produced by the motion of this coil inside that magnetic field, that is represented by VLV, and already we discussed. Now we will discuss the application part of this, means if we are connecting a bulb across this coil, and now this is a rod, conducting rod, that is moving onto this rails with velocity V. Already we know that we want some potential across this bulb. This can be produced due to the motional EMF, that is E. So BLV by this value, it is the induced EMF. So we can say this is just an EMF appeared or in EMF supplied to this bulb. We want to find out current across this, so we can be I is equal to VLV upon resistance R. I is equal to E by R, that is equal to BLV by resistance R. L is the length of the conductor, this part. V is the magnetic field strength into or out of the plane, and V is the speed with which it is moving or it is changing the area. So means we can say the current on the horizontal bar is in the magnetic field, so it is experiences a force opposite to the gravity. This can be the application under gravitational effect. Now we will discuss some example based on this concept. Now first of all I will read the question, that is, a metallic rod of length 1.5 meter long rotates about its one end in a vertical plane at the right angles to the magnetic meridian. If the frequency of rotation is 20 revolution per second, find the EMF induced between the ends of the rod. BH is the horizontal component of Earth's magnetic field. So first of all we will note down the given data. First, the magnetic field strength BH, that is equal to B, and it is given as 0.32 into 10 to the power minus 4 Tesla. Length of the rod L is equal to 1.5 meter. Rotates about its one end in a vertical plane at right angle to the magnetic meridian. Means angle between the area vector and magnetic field vector is 0 degree. So this is it. Now if the frequency of rotation is 20 revolution per second, that is F is equal to 20 revolution per second. Now we have to find induced EMF across the ends of the rod. Okay, so means it's about, there is a rod that is rotating about its, we need to understand E is equal to V LV, because it is a case of Motional EMF, and V equal to L, and V is equal to L into omega. We know that V is equal to L into omega, and we are getting V L square into omega this time. Omega is the angular speed, that is equal to B L square 2 pi into F whole square. So it is E is equal to B into L square into 4 pi square into frequency square. On substituting the corresponding values as 0.32 into 10 to the power minus 4 multiplied by the length as 1.5 meter square multiplied by 4 into pi square is taken as approximately, we need to assume pi square equal to 10. We are assuming this one, assume. So it is 10 and then frequency, that is given as 20. So when we will solve this value, it would be around 6 point something like that. So this is the method to solve this question, and we will put the corresponding values over here, VL square, 4 pi square, F square, and this would utilize the corresponding terms over here. In this part we discuss about applications of Faraday's law of electromagnetic induction, Motional EMF concept. So in the next part we will discuss the self-induction concept, application of Lenz's law as conversion of mechanical energy into electrical energy. So stay tuned with us.